So this is the topic. I'll explain what discrete tori are at some point. Okay, so let's start with the general question of bounds on binary codes. So an error-correcting code of lengths n and distance d is a subset of the discrete cube, such that for any two distinct points, the distance between them is at least d. It's a Hamming distance. So it's basically a packing of disjoint Hamming balls of radius d minus 1 over 2. And we want to know how well we can pack, what's the largest cardinality of such packing. And the range of distances d we are interested in is linear in n. So fix a parameter delta, and d is delta n, where delta is between 0 and 1/2. In this range, it's easy to see that the packing would be exponential in n, depending on this parameter delta, and what we don't know is what this exponent is. It's a big open question. Corresponding to this big open question in Euclidean geometry is the optimal density of packings of Euclidean balls. It's very similar, and the techniques are essentially the same for bounds. Right, so this is a big open question. We won't solve it in this talk. Okay, but let's talk a bit about bounds. So these are the simple, classical bounds on the sides of the packing. So the upper bound is just the volume argument, right? So we want to pack disjointly balls of radius d minus 1 over 2. B is a Hamming ball. This is the radius. So the best possible packing is at most the size of the space, divided by the size of the object we want to pack. And the lower bound you can get by a simple greedy argument. So you take a point, put it into your packing. This is the center of one of the balls. You throw away the ball around this point. You still have some space left. You take another point, throw away the ball around this point, and this is what you'll get. So taking logs out of this, we get these bounds on the exponent. This is between 1 minus the binary entropy of delta and 1 minus the binary entropy of delta over 2, where this is the definition of binary entropy, which everybody knows, of course. And we use the fact that the cardinality of the Hamming ball is 2 to the entropy of its radius over n times n, up to negligible factors. Right, so these are the simple bounds. And the best known bound, at least for about half of the distances, delta, is this bound due to a Michaelis, Rodemich, Ramsey, and Welch from 1977, following the linear programming approach of Delsart. So this is a bound, and notice that something strange is going on because we have the cardinality of a packing bounded from above by a cardinality of a Hamming ball, right, in the exponent, which is kind of weird. We bound this sort of, size of epsilon at a dispersed object, right, by this very dense object, and some duality is involved somehow, and we'll get to it. Right. So we have this, and this bound is the best known. It's not optimal. It's the best known for deltas between 0.273 and 1/2. Right, so in this talk we only discuss linear codes. This is a special class of codes. So it's a packing whose centers are a linear subspace of the cube, and it has many similarities to lattice packings in Rn instead of regular packings. This is obviously a more structured setting, but unfortunately the bounds we know exactly the same. We don't have any better bounds for those. And so what can you do? We want to improve the bounds. And, we don't know how to improve the bounds, so at least we want to understand the bounds better. So, so let me tell you briefly how do you prove linear programming bounds. So this is how we prove linear programming bounds. You take a combinatorial problem, you embed it into this algebraic setting of association schemes, you get some linear inequalities, you use linear programming relaxation, you use LP duality, you get to extremal problem in univariate polynomials, you use orthogonal polynomials to solve it, and you get of course, you shouldn't be able to understand this, so it's complicated, right? This is the way you prove linear programming bounds. So, but we do have a much nicer proof of this bound due to Friedman and Tillich from 2002 for linear codes. So let me tell you about this. So we have a code, a packing, in the n-dimensional cube with minimal distance d. So what we consider this quotient space, T, which is f2 to the n divided by the dual code. So C perp is a orthogonal subspace. And we want somehow, at least intuitively, to think about this. This is a discrete torus. We are talking about, similarly to if we divide Rn by lattice, we get a continuous torus. Right? Linear algebra tells us that the size of T is exactly the size of C. So we want upper bounds on T. And, okay, questions? Okay. So we think about this torus as a metric space, as a Cayley graph. Well, it's a quotient group. We have addition, and taking the unit vectors to be a genetic set, we get a Cayley graph. We can assume, without losing anything, that all of these are distinct. So we get an n-regular graph with this adjacency relation, and it's a Cayley graph. It's a nice vertex transitive graph, and we want to know how large it is. So we want some, tools to be able to understand how large this graph is. So here is a couple of examples just to get a feeling on what can you expect from what kind of graphs do you get. So let's take C to be the Hadamard code. So here n is 2 to the k minus 1, and this is a generating matrix of C, and I'm writing here all the vectors of length k, all the non-zero vectors of length k. Right. So this is k, and this is n. So what would be, so I'm looking at the T, as this torus T, which is f2 to the n divided by C perp. So what's the graph? This is a question from the audience.
T, f2 to the n divided by what?
By the Hamming code, by the orthogonal subspace. It's not a tricky question.
What is the question? What is the graph?
Yeah. So it's an n-regular graph on 2 to the k points, which is n plus 1, so it's a clique, right? So this is easy. What about sum of two Hadamard codes on these joint subspaces, so you get a graph product? It's kind of easy. So you sum things, you get some graphs.
Alex, can this graph have parallel edges? Or
it can if you have repeated coordinates, but it's sort of not very interesting, right?
But that's the only way.
I guess. Right. So we want to know how large this graph is, and we want to grow, to see this, we want to grow neighborhoods around some point. It's a vertex transitive graph around 0. Right, so SR is a sphere of radius R around 0. This is basically the set, what it corresponds to, the set of cosets of C perp with coset leaders, which are vectors of minimal weight, exactly R. Think about this, right? So we're looking at shifts of the dual code of the orthogonal subspace, such as the minimal weight of a vector in this affine subspace is exactly R. And we want to know, we want to understand how fast these unions, the metric balls around 0, the unions of the spheres grow. Right? So we want to know how many cosets, how many points we have on each sphere. And this is known in coding theory as understanding weight distribution of coset leaders. How many points of each weight do we have in this torus? And unfortunately, this is a notoriously difficult question in coding theory. Understanding the weight distribution of coset leaders, even for some simple subspaces, some simple codes, it's very difficult. Right, so Friedman and Tillich avoid this problem, dealing with this problem directly, and they deal with the torus T only by using comparison theorems. Sort of the intuition somehow comes from Riemannian geometry, comparing to the one sort of constant curvature if you want space, the Boolean cube 0, 1 to n. So I'll give you the proof. So we have that the size of the ball of radius r around 0 in the torus is at most this in the hemicube, which is just a projection, right? This is simple. And we also have a more surprising inequality, so I'll explain what it means. So the Laplacian eigenvalue, or the Dirichlet eigenvalue of this ball in the torus is at most this in the cube. So what does it mean? So a Laplacian eigenvalue of a subset is the minimal Rayleigh ratio for, of the Laplacian, which is the usual graph Laplacian, for functions supported in the subset. Okay, so I'm taking functions supported only in the subset. and I am looking at, at the Rayleigh ratio. So f is supported in omega. I'm looking at this divided by this, and I want minimum. Right, for all non-zero f's supported in omega. So notice that the larger the set is, the smaller its Laplacian eigenvalue. So if I take everything, I can take the constant function, and I get 0. Right? So this inequality is somehow surprising, the combination of these two, because the ball in the torus is smaller than the ball in the cube, but its Laplacian eigenvalue is smaller. So how this could be true? Question to the audience.
They're the same.
No, there are two different Laplacians in two different spaces, right? One of them in the torus and one of them in the cube.
But
And
if you undo the projection, the ball of radius r in the torus corresponds to
a union of balls,
to a larger number of
yes.
elements.
So
of
and
the
then you will
vector.
have an equality in the Laplacian eigenvalue. Okay. So and this corresponds somehow. The intuition of Friedman and Tillich came from this theorem, comparison theorem of Cheng in Riemannian geometry, which basically states the same. It's not hard to prove. Right. And now we are almost done. So and the last thing to observe is that the Laplacian eigenvalues in this torus, so the first eigenvalue is 0, but the second is 2d, twice d, because we know what the eigenvectors are. The eigenvectors are the characters of the cube supported in the space C. And because the minimal distance space C is d, the minimal eigenvalue is large. It's a very simple thing to see. So since the second Laplacian eigenvalue is 2d, if you have a set whose Laplacian eigenvalue is smaller than 2d, smaller by some fixed amount, say at most 2d minus 1, then by Cauchy-Schwarz we get that this should be almost the whole space. So we are done. So choose a radius r. Question?
No, we are done with what? With proving...
Basically, with proving the eigenbound, the bound. Yeah, yeah.
For the code.
Yes,
Upper bound.
the upper bound.
But how we are done?
So I'll tell you. Yeah, thank you, Gil, for the question. So choose a radius r so that the Laplacian eigenvalue of the Hamming ball in the cube is at most, say, smaller than 2d minus 1. This we can do because this is an easy computation, which they do, but this was also done before. Basically, this is to bound this Laplacian eigenvalue is exactly to compute the location of the first zero in the appropriate zonal spherical function, the appropriate Kravchuk polynomial. This is what you do. This is basically solving a quadratic equation. Then we know that the first Laplacian eigenvalue of the corresponding ball in the torus is at most that in the cube is smaller than 2d, and therefore the size of the code is basically the size of the code is the size of the torus by linear algebra. This is by these Laplacian eigenvalues is almost the same as the size of this ball in the torus, and this is smaller or equal than the size of the ball in the hemicube, and we are done. Right? This is the proof. Right, very nice. Questions?
Why was the size of omega the same as the size of the torus?
Because, so look at so you're talking about this, right? I can't use this mark. It went somewhere, this red point. So because if you look at the characteristic function of omega and just write it out as a combination of characters, right, of the eigenfunctions. So where do you get the contribution? How do you get such a small eigenvalue? Because you have to have large unit product with all one function, basically. And then you're large.
So this gives the best...
This gives the first linear programming bound, which is the... Yeah.
And this can be extended to the other...
I don't know. And this is also only for linear codes, right?
And this is only for linear.
Only for linear codes.
It cannot be extended for...
It can. Okay. So, right. So let me, have one slide which I didn't have originally as an aside on other proofs and extensions. This follows the question of Gil in the first lecture in this workshop. So if you look at this proof, you see that this, should have some Fourier analytic, interpretation, because, the eigenfunctions of the torus are characters and so on, and one should be able to do something. So to be more precise, this is not exactly the proof we saw, because this is not exactly the proof presented in Friedman and Tillich. That one is rather long. This is kind of a streamlined version of the proof. So, but one can come up with a Fourier analytic proof, which sort of doesn't have to look at the tori. It works only with the cube itself, and therefore it has all kinds of extensions. So, for instance, we immediately get the same not only for linear codes, but also, so we basically have proved that the code is small, equivalently the dual code, the orthogonal code is large. And the orthogonal code is a d-wise independent set, because the distance in the code was d. But one immediately gets more, that the d-wise independent sets, which do not come necessarily from linear codes, are also large. And also by some analysis, one extends this to general binary code, not only linear codes, because you don't need these quotient objects, right? And also so that one was with Michael Navon, and the other thing, the other extension was Noah Edelstein. So you can prove similar bounds for designs in many symmetric spaces, which are graphs and Riemannian manifolds with many symmetries. And so design is a finite set of points on which all the simple eigenfunctions of the Laplacian corresponding to small eigenvalues vanish and average. So you sum them over these points and they vanish. So you can have spherical designs on the sphere or d-wise independent sets and so on. So the proof goes like that. So you have this design in your symmetric space, and you start to grow neighborhoods around points of this design, and for a sufficiently large radius, you cover almost everything. And therefore, you have a bound in this radius, so therefore your set of points is large. And this gives a uniform proof of the bounds on designs, which were proved, in several papers, like starting from the 70s till 2009 or something, in projective spaces, in spherical, on the sphere, and so on, and in various graphs. Okay, so
For the sphere?
in for the sphere as well.
What do you get? What bound?
You get a bound. It's an exponential bound.
Because now we know the truth.
Yeah, but we still don't know what the exponent is. The upper bounds before that were double exponential, were 2 to the n squared or something. Now they have a simple exponential, but the exponent is still unknown. Okay, so look at this. So now, how is it related to the question of Hamed and Gill on isoperimetry if you start from a d-wise independent set? So suppose this is a cube, right? The cube. You start from a d-wise independent set. You start to grow neighborhoods. It turns out that the growth is faster. The growth is faster than what you get from looking at hyperconductivity, say, applying noise. Because if you just look at estimates you get from hyperconductivity, you get worse bounds, worse than linear programming. So you do have some advantage if you look at d-wise independent sets. And if you can improve this advantage, you'll get better bounds for at least for linear codes, which would be very nice.
This answer Hamid question about
It-
KKL for
Somehow, it tells you that there is something slightly better, but it would be hard to improve, because then you'll solve, or at least improve significantly somehow, right? Okay. So, right. But now going back to this proof of Friedman and Tillich, what can we learn from this proof? So it's good to be able to control growth of neighborhoods of balls in the tori. And if we can, so this is this big thing about this proof. If we can show that actually these equalities hold with inequality, either the metric balls in the torus grow slower, or the eigenvalues are smaller, we can beat the linear program bound. So this sort of gives you, a way to try and improve linear program bounds. So we have thought about this for quite a while, and we can do it. We don't know how to do it, but we can do some simple things. So let me give you an example. One can improve the best known bounds for LDPC codes. These are low density parity check codes, which means that their dual codes, the dual subspaces are spanned by constant weight vectors. Suppose weight 3 vectors. Right? So the claim, so we can ask ourselves how large this code could be. So we now have a linear packing of Hamming balls in the discrete cube with an additional structure. So the structure is that the dual space is spanned by low weight vectors. And we have bounds. So there are bounds by Burstein, Krivilevich, Litzin, and Miller in 2002, and Ben Chaim and Litz in 2006, improving linear program bounds because we have additional structure. And what we are going to prove that, in fact, in this case, we can show that the metric balls in the torus grow exponentially slower than those in the whole space, and therefore we get an advantage. Great. So this would improve the bounds for almost all distances. And there is a proof here, but let me give you a very simple proof, at least for the case of 3. So the dual subspace is spanned by vectors of length 3. So let me show you how we can prove it. So this is the torus, this is 0, and now I'm looking at two spheres of radius r and radius r plus 1. So I want to look at this picture compared to the corresponding picture for the Hamming cube. This is 0, 1, 2, 3. So how fast do the neighborhoods grow? In the Hamming cube, we know exactly. For any point here, for any point x here, we have, so how many points we have going outside, going further away from 0, right? So these are the points. So this is a point of weight r. This is exactly the points at distance 1 of weight r plus 1. So we have n minus r points, right? We have n minus r points going out, and we have r points going down. This is the geometry of the cube. So I'm going to try and convince you that here, for any point x, we have only n minus, at most, n minus 2r points going further away from 0. And this will tell us immediately that these balls grow exponentially slower. And why is that? So look at a point x of weight r. So take a coset leader, a representative in this coset of weight r. So through each point of this set of the support of x, we have a linear dependency of length 3 passing through it, and it passes only through one point of it. Otherwise, we'll get a shorter representative, if you look at it for a second. So now I claim that if I go in any of these directions, I don't go up by a trivial linear algebraic thing. And so I won't do it. It's very, very easy. And the union of all these R sets, each of them is of size 3, is of cardinality, again, very simply, at least 2R. So in all these directions, I do not go up. So I should either stay on the sphere or go down. And this is it. Right? So it's very simple. OK. So this is useful. A very simple example. OK. So this is a proof which I don't want to show. OK. So this was a very simple application. Now we can forget about linear programming bounds and just ask ourselves, how can we control, we have this graph. How can we control the growth of metric balls in this graph? Right? So how? So we are going to try to use this intuition of Friedman and Tillich that this point of view of Riemannian geometry is nice. So in Riemannian geometry, they do have tools to control growth to prove upper bounds on growth of neighborhoods of a point by using curvature. So we have this notion of Ricci curvature in Riemannian geometry. And this notion allows to compare the rate of growth of neighborhoods of a point and of eigenvalues of these neighborhoods between a constant curvature space and between spaces which do not necessarily have constant curvature but have at least the curvature of the constant curvature space. So, and the lesson to take from it, we have high curvature, the metric balls grow slowly. So we want to find a notion of curvature in graphs that will allow us to do this. Right, so we are thinking about the discrete torus as a discrete manifold, right, and want a notion of discrete curvature. So one can look for such a notion in the literature, and there are several notions. There is one due to Olivier, there is one due to Villani, and probably some others, and the one due to Olivier is easier. This is the one we are going to use. So now let me tell you so we have changed the topic, right? We spoke about linear programming bounds, and we are done with that. We slightly improved linear programming bounds for some simple codes. And now we want to forget about all this, and we speak about general graphs and bounds on growth, of neighborhoods of points in these graphs, and we wanted to use this notion of curvature. So the intuition, I'm going to define this. It's a very simple definition, and it tries to capture the following intuition, that in a flat space, when flat metric space, when the curvature is 0, it sort of says that I can shift points in parallel. So if I have two small balls around 2 points, I can shift. I have a parallel shift, and the distance between the balls would be exactly the distance between the centers, the average distance. And if you have, negative curvatures, then sort of balls grow further apart. It's somehow like that. And in a positive curvature, they grow together. And therefore, the growth is slower. This is the intuition I want to try and capture. So now we have an n-regular graph. And for a vertex of this graph, consider a uniform probability measure on this vertex and its neighbors. So we have a point x. It has n neighbors, and we define weight 1 over n plus 1 on any point, including the center. Okay. So, and now I know I have the notion of distance. This is just the usual distance defined by the graph. Now I want to define the notion of distance between two distributions on these balls, which will try and capture the notion of average distance between these balls. And this is very simple. So I'm looking at all the possible ways to match points in this ball around x to points in the ball around y. And I'm looking at the expectation of the... So now I'm moving points in one ball to the points in the other ball. And I'm looking at the average work I'm doing, the average distance. Okay? Is this clear? It's not... Yeah. So let me just say that usually we are considering, so this is this Wasserstein distance, the distance between distributions. We are doing the same, but according to any distribution on a product space whose marginals are M1 and M2. But here it's easy to see that we need only to consider matchings.
So M,
Yeah.
M is a matching, not a bijection, right?
M is it's bijection, right? Yeah. Right, so we have this. Right, so, and we define this notion, Olivier defines this notion of coarse Ricci curvature between x and y to be this. This is kappa between x and y. This is a function of on 2 points. This is 1 minus the average distance between the balls defined by the distance between the centers. So, if the distance between the, metric between the neighborhoods of x and y is greater, its average distance is greater than the distance between the centers. This is negative curvature. If it's the same, it's 0. Otherwise, it's positive. Okay, so and for a graph, we set the curvature of the graph to be the minimal curvature between points, any pairs of points. Is this okay? Okay. So let's see some examples. So I claim that the Cayley graph of an abelian group is non-negatively curved. And this is trivial because I have a parallel shift rate. This is very easy. A regular tree is negatively curved, actually, and this sort of gives additional meaning to this notion that a tree is a hyperbolic space. And we can ask...
Is it true that any hyperbolic graph has negative curvature in this sense?
Probably.
Okay.
I don't know. Right? This is everything is sort of very, very easy, right? The first approximation thing somehow. So what about the Hamming cube? So it's a very simple observation that the curvature in any graph is attained at adjacent points. This is just a consequence of triangle inequality. Question?
So one kind of general complaint from the public is that this is completely standard notion of contractive coupling for simple random walk. It existed long before Olivier.
He says something about it,
just
actually.
called it a different name, but there is nothing new in the concept. It's exactly coupling of one step of a simple random walk that you have, that you can contract with this. That there is and this fact you just mentioned, is known in computer science under path coupling. It's exactly so. It's and he did it much later.
So I'm very happy to hear. So there is much known about this, probably more than Olivier writes. Okay, good.
You in another field
No, it's not really another field.
by another person.
No, but
I think I'll continue. Okay. Right. So this notion. Right. Sorry. So what about what I'm doing? Curvature in the cube. Right. What about the Hamming cube? So the curvature is attained at points of distance 1, and in the cube, the neighborhoods of any 2 points intersect in two spaces, in two neighborhoods of any two adjacent points, x and y, intersect exactly in x and in y. I can't draw it for some reason. You probably believe me. This is x, this is y, these are the neighborhoods, right? Both x and y are in the bold. So, great. So this tells us that our matching doesn't have to move 2 points. X and y stay in place, right? And we define this matching very easily. So the transportation distance, we only move n minus 1 points, distance 1, and therefore, it's n minus 1 divided by n plus 1, and the curvature, is at least 2 over n plus 1, but we can show it's very easy to see it. So it's easy. So what about Tori? So obviously the same argument also holds for a torus, and the curvature is at least this, but maybe in some cases we can have more. So can we do better? And curvature is a local notion, so we want local constraints. If we have local constraints in our codes, we will get better bounds on the curvature.
Excuse me. So
Sure.
You said the curvature in any graph is a thing that's like points of distance 1?
Say it again?
The curvature is a thing that's points of distance 1? Is that some average?
Yeah.
value?
It's just by triangle inequality.
Okay.
It's very simple.
And locally the torus looks just like
The cube, yes.
Like the cube.
Well, let's see. Okay, so it depends on the subspace, right? So we want local constraints. So let C be a code with a local constraint of length 3, meaning that C perp, the orthogonal subspace, contains a vector of length 3. What can we say? Right, so we want to get a non-trivial bound on curvature. So suppose this constraint contains coordinate I. So then I claim that the neighborhoods of x, if y is x plus ei, I go in direction I, they intersect in 4 points. So if the constraint contains points I, j, and k, then I claim they also intersect in x plus j and x plus ek. This is very simple. It's immediate. And in general, if we have t vectors passing through i's coordinate of length 3, then the curvature in this direction is at least the neighborhoods intersect a lot, so these balls somehow are glued together in many points, and therefore the curvature is at least 2t plus 1 divided by n plus 1. Right, so everything is going to be very, very simple. Right, so great, so we have this, we sort of understand this. So now we are looking for examples of locally constrained codes, and we have in computer science many such families. We have locally decodable codes, locally testable codes, locally correctable codes. We'll talk about locally correctable codes. I already heard, talk by Shubhangi yesterday about this, about the notion of locally correctable codes. Right, so a linear code is locally correctable with 2 queries if for any coordinate it has many vectors of length 3 containing this coordinate. Right? So, and here's a theorem of Ben-Sasson and Eli Ben-Sasson and Michael Widerman from 2009. Assumes that we have many vectors of length 3 passing through any coordinate of our code, and assumes that there are no repeated coordinates in our code. So the dual code contains no vectors of length 2. Then we have this bound. The cardinality of the code is at most this, up to a logarithmic factor, right? Sorry, up to taking logs on both sides. So so I guess that if this number tau is a constant, so we have linear many vectors, this was already known, but I think that for some range of values of tau, this was not known for tau. This is explained in the paper of Michael and Eli. So the proof goes like that. So you reduce to locally decodable codes, which is a weaker notion, and you use some variation. You prove a new variation of the edge as a parametric lemma, which is it requires a certain amount of work. So let us try and prove it using this curvature thing. So what do we know about graphs with high curvature? So intuitively, they should be small because metric balls grow slowly. In fact, they actually stop growing at some point. And this is what is stated by the Bonnet-Myers theorem in Riemannian geometry. So if you have a manifold whose curvature is bounded from below by that of a sphere, of a constant curvature, a manifold, then its diameter is at most that of the sphere. And we have Olivier or maybe some other people we have this discrete version of this. Suppose we have a graph of curvature, any metric space, any discrete metric space, say, of curvature kappa, then the diameter of this graph is at most 2 over kappa. So let me prove it. This is a very easy statement. So, right, so suppose we have 2 points at distance d in our space, and I want to bound this distance. So this distance is capital D. And I want an upper bound of 2 over kappa on this distance. So I'm going to bound this distance from above. Sorry, I'm going to bound the amount of work which will take me to move, the uniform distribution on the neighborhood of x to the uniform distribution on the neighborhood on y. I want to bound it from 2 sides. So on one hand, I claim this is upper bounded by 1 minus kappa times d. Because, kappa is, so this is by triangular inequality. So to move 1 in this direction takes me 1 minus kappa. This is the amount of work by definition. And by the triangular inequality, this is this. On the other hand, I want to bound it from below. So this is at least, by the triangular inequality, the distance between this measure mu x and the delta measure at x. I don't want this. I want the distance between 2 delta measures, delta x and delta y, minus the distance between delta x and mx, minus the distance between delta y and my. Is this okay? Now the distance between delta measures is d. This is trivial, this is d, and the distance between 2 distribution measures, 2 probability measures, sort of supported distance 1 is at most 1. So this is at least d minus 2. So we get that 1 minus kappa times d is at least d minus 2, and we are done. Right? Very easy. So the diameter is at most 2 over kappa. Great. Good. So how are we going to use it? So here's a proof. So so recall this claim of Ben-Sasson-Widerman. We have that through any coordinate pass that many vectors of length 3. Consider the torus. The curvature is at least 2t plus 1 divided by n plus 1, as we have noticed. Therefore, the diameter of the torus is at most n plus 1 divided 2 over kappa, which is this. Therefore, the cardinality of the code is that of the torus, which is at most the cardinality of the ball of radius n plus 1 divided by t plus 1 in the torus, which is at most the cardinality of the corresponding ball in the Hamming cube, and we are done. Right, so this is the proof. Okay, very simple. And so things get more complicated when we have multiplicities for some reason. Okay, right, so an additional fact is, so we proved that C is small because the torus has small diameter, which is equivalent to the fact that the orthogonal code has a small covering radius. So you can get near every point in the Hamming cube by a point in the orthogonal code, right? Therefore, it's very large. Therefore, the original code is very small, right? So this is the proof. And somehow the trouble in these locally constrained codes happens when you allow repeated coordinates, and things become much more complicated. And Eli and Michael proved if you allow repetition of coordinates, but each coordinate repeats equal number of times, they prove this bound with more work. But in our case, the same argument gives actually a tight bound, which is slightly better. So now, if we have k equivalence classes of coordinates, then we are looking actually at a graph, a k-regular graph, but with parallel edges. So there are n edges, but only k of them are different. And we consider the induced measure on neighborhoods of points given by this. So it's not a uniform measure anymore, but again, one computes the distance and one gets the bound. So everything is very simple. And, well, so I am actually, running out of slides, not out of time. Sorry, yeah, well, I still have like 3 minutes, right? So we can do the same with a result of Reed-Dinur and Talley-Kaufman on locally testable codes with large distance. Again, it takes a non-trivial amount of work to prove bounds, and with this notion of curvature, it's basically immediate. And I guess, well, we can do slightly more. Let me just say that, since I have another minute, that what happens with the really sort of interesting questions when there are more than two queries, right? This is hard. And there we have a very simple argument which gives a bound using this curvature notion, which is better than what Katz and Trevisan got using the information theoretic approach, but worse than what Kernidis and de Wolf got using quantum information theoretic approach. So it's in between, somehow for some weird reasons. And I'm done. Right?
Any questions?
So this approach seems to be working with local constraints because the notion of curvature is
Yes.
just based on very small neighborhoods.
Sure.
Oh, and so is there something that works
So
with
we were
larger
hoping, right, at least with three queries, right? So this notion of Wasserstein distance is like using somehow this amount of work you move, like so. And the question is, can this be done in a smarter way, right? And hopefully yes, but we don't know how. Right? Flows from there to there, right? Moving mass around, but.
Any other questions? Well, thanks again, Alex.